Hello everyone, this is the lecture number 31 of the lecture series of Naval Architecture made for MEO examination. In this lecture, we will continue with the transverse stability of the ship. Specifically, we are going to cover numericals on the free surface effect. Let's start the first numerical on the free surface effect. A ship of 8153.75 tons displacement, it means this is the total weight of the ship, let me call with a W1, has a km is 8 meter, kg is 7.5 meter and has a double bottom tank 15 meter length. The length of the double bottom is perpendicular to the screen, 10 meter wide and 2 meter in a depth, which is full of salt water ballast. Find the new GM if this tank is now pumped out till the half empty. So how to proceed for this numerical? First thing you have to understand here, there are two things are happening here. Initially the double bottom is completely filled with the ballast water, and including the weight of the ballast water as well as a light weight of the ship, the total weight of the ship is 8153.75 tons. Let me call that is a W1, 8153.75 tons. This includes the weight of the ballast water which is there in a double bottom. Now what we are doing now, we are removing or we are pumping out half of the water which is there in a double bottom. So what we have to do, you are removing some amount of the water from the double bottom. It means that it's like you are removing some weight from the double bottom. So if you are removing some weight from the double bottom, what will happen? Because of the removal of the weight, there will be a rise of the center of gravity from the G to G1. This is happening because of a removal of the water or because of a pumping out the liquid from the double bottom. But when the water is pumped out, so double bottom is now having the free surface effect. And because of the free surface effect, there will be some virtual rise of the center of gravity, and that will be from G1 to GV. So this example contains both the things. The first thing is, the first effect is a removal of the weight from the double bottom. Because of that, there will be a rise from G to G1, and after a removal of the water, there will be a free surface effect generated because of the partially filled double bottom tank. Because of that, there will be a rise of a center of gravity from G1 to GV. So first step, what we have to do, we have to find out the weight of the water which is pumped out. Now what they are saying, half of the water is pumped out. It means that first of all, find out what is the weight of the half water which is in the double bottom. So the depth of the double bottom is 2 meter, the beam of the double bottom is 10 meter and the length of the double bottom is 15 meter. We are removing half of the water, means we are removing the water up to the 1 meter from the top. So this much amount of the water we are pumping out. So we have to find out the weight of that water. So how to start for that? So let me call the weight of that water which is pumped out, that is a W. That is equal to volume of the water multiplied by density of that water. In this case it is a salt water, so it will be, the volume is length of the double bottom multiplied by beam of the double bottom multiplied by half depth of the double bottom, that is let me call D by 2 into the density of the salt water. So it will be, length is 15 meter, beam is 10 meter and the depth 2 by 2 into 1.025. So like this you can calculate the weight of the liquid which is pumped out, it is coming 153.75 tons. Now, where will be the center of gravity location of this weight? So that will be at the half of the depth which is pumped out. The total depth of the water which is pumped out, it is 1 meter. So center of gravity will be at the half only. It means from here to here this distance is a 0.5. But I want the center of gravity location of this pumped out water from the keel. So it will become from keel to up to this distance is 1 meter plus the 0.5. So the location of the center of gravity of the water which is pumped out, let me call kg, that will be 1.5. So we know the weight which we have removed, we know the center of gravity location of that mass which is removed. Then how to proceed for that? You need to find out the new center of gravity location, that is a kg1. To calculate kg1 because of the removal of the weight, you need to create a table like this. The first column is a weight, the second column is a lever, and the third column is a movement. So first number in the weight column, that is 8153.75, that is the weight of the ship. The location of the center of gravity of the ship from the keel is 7.5 meter. Then the second weight, that is minus 153.75. Why we have taken as a minus? The reason is because we are removing the weight. That's the reason we have taken the weight as a minus. Then lever of that weight from the keel, it is 1.5 meter. So do the multiplication of column number 1, that is a weight, into the lever. You will get the movement like this. Do the algebraic summation of the movement. You will get the summation of the movement is here. This is the summation of the weight. To calculate the new center of gravity location from the keel, that is kg1 is equal to summation of the movement divided by summation of weight, that is coming 7.6153 meter. Once you got the location of a new center of gravity, that is g1, when you remove the mass of the water, or when you pumped out the water, then you will find that there will be a partial fill of the double bottom tank. Now because of the partial filled tank, there will be a free surface effect over here. So how to calculate the free surface effect? So because of the free surface effect, the new center of gravity will come, that is a GV. So now you have to calculate G1 GV. So how to calculate that? G1 GV is equal to I is the moment of inertia of the tank top divided by the displacement of a ship when the center of gravity of the ship is at a G1. It means after the removal, after the water is pumped out, that time what was the weight of the ship, that is equal to the displacement of the ship, that is the W2 into the density of the liquid which is present in the double bottom, that is a salt water in this case, into 1 by n square. Now how to calculate the value of I? I is equal to LB cube by 12. L is the length of the double bottom, that is a 15. B is a 10 meter, that is 10 cube divided by 12. Like this you can calculate the I. Then what is W2? W2 is equal to W1 minus the weight of the water which is removed. It is coming 8000 tons. Now rho is 1.025 tons per meter cube. Always keep in your mind, take the density in tons per meter cube. The reason is W which we have taken, that is in a tons. Now coming to N. N is a number of compartments longitudinally. Now in this case they have not mentioned anything about compartments. So if nothing is mentioned about the compartment, you have to take N is equal to 1. They have not mentioned anything about the center girder or anything. Nothing is there. So this whole double bottom is only a single compartment only. So take N is equal to 1 here. If you substitute all these values here, you will get the value G1 GV is equal to 0.160 meter. Now if you want to calculate the new metacentric height, that is GVM, that you can calculate like this: Km minus Kg1 plus G1 GV. If you substitute all the values here, that is Km is 8 meter, Kg1 just now we have calculated, that is a 7.615 plus G1 GV is 0.160. If you substitute all the values, you will get the value of a new metacentric height, that is 0.225 meter. So like this you have to solve this numerical. Let's start one more numerical to understand the free surface effect. A ship of 8,000 tons displacement, it means you can say weight of the ship, has a km 7.5 meter and the kg is 7 meter. A double bottom tank is a 12 meter long, 15 meter wide and 1 meter deep. The tank is divided longitudinally at the center line. It means that there is a center girder and both the sides are full of salt water. Calculate the list if one side is pumped out until it is half empty. Let's start the solution of this numerical. The first thing which they have given, the displacement of the ship is given, that is let me call W1 8,000 tons. Km is given, kg is given. A double bottom tank is a 12 meter long, 15 meter wide and 1 meter deep. So this is 1 meter deep and 15 meter wide, and the length of the double bottom is perpendicular to the screen. The tank is divided longitudinally at the center line. So there is some center girder here. It means that if you think about the number of compartment or the number of tank here, it will be the whole double bottom tank is divided in 2 compartments. So n is equal to 2 here in this case. Now what they are saying, calculate the list if the one side is pumped out until it is half empty. What they are doing now, they are removing the water from only one side. Let me consider that one side means I am removing the water from the starboard side somewhere here. So this half of the water I am removing or pumping out. So depth of this water is a 0.5 as the total depth of the double bottom is 1 meter. So if you are removing, it's like you are removing the weight from the starboard side. If you are removing the weight from the starboard side, what will happen? There will be a 3 conditions going to occur here. The first condition is because of the removal of the weight, there will be a vertical rise of the center of gravity, that is a G to G1. But whatever the weight you are removing, whatever the water you are pumping out, it is not from the center line, it is from the starboard side. So center of gravity of this water which is removed, that will be somewhere here. So the new center of gravity which will become, that will be in the inclined direction like this. So this is the new center of gravity after pumping out the water. To calculate this, what we are going to do, we will calculate the vertical shift of the center of gravity. At the same time, we will find out the horizontal shift of the gravity. It means that you are calculating the G2 directly. So how to proceed for that? So we will find out the first new center of gravity G1 because of the removal of the mass. Then we will calculate the G1, G2 because of the removal of the mass from the starboard. Once you remove the mass, as this mass is a liquid, there will be a free surface effect in the starboard side of a double bottom tank. So because of that free surface effect, there will be a virtual rise of the center of gravity from G2 to GV. So the new center of gravity will be at a GV. So this G2 and GV projected on the center line, and that will be equal to G2 GV is equal to G1 GV. Both are same in a magnitude. So let's start the calculation for calculating the new center of gravity Kg1. Now before starting the calculations to calculate the rise of the center of gravity from G to G1, that is from the keel it will be kg1. You should know how much amount of the water we have pumped out from the starboard side. So to calculate that, let me call it a small w. That will be total length of the double bottom into the half of the width of the total ship, that is the width of the double bottom. Then the d by 2, that is a total depth by 2, means the total depth is 1 meter. The half of the water which we have pumped out, that will be 1 by 2, that is your d by 2 I have written here, into density of the salt water. If you substitute all the values here, you will get the water which is pumped out, that is 46.125 tons. So this much amount of the water is pumped out. Now with the help of this, we are going to calculate the rise of center of gravity G1 from the keel. So for that purpose, you have to create again the column like this: weight, lever and the moment. The first component, that is 8,000 tons, the total weight of the ship. The center of gravity location from the keel is 7 meter. Then take the moment, 8,000 multiplied by 7, you will get a 56,000. Now the weight of the water which is removed, take the sign here minus into the lever, that is 0.75. How this 0.75 is coming? Now the center of gravity of the mass which is removed, that will be half of its depth. The total depth of the water which is removed, that is a 0.5. So the center of gravity will be at 0.25 from the top of this water removed. Then from the keel it will be 0.5 plus 0.25, it will be 0.75. That we are substituting here. Then do the multiplication, weight into lever, you will get this much as the value. Do the summation of the moment, do the summation of the weight, calculate the new center of gravity location from the keel. It is coming 7.036 meter from the keel. So this value which we got now, that is 7.036 meter. Now let's calculate the horizontal shift of the center of gravity, that is G1, G2. So how to calculate that? For that also you have to create the table which I have already prepared here. So first column is a weight, second column is a lever and the third column is a movement. So to calculate the horizontal shift from G1 to G2, we need to take the movement about the center line of the ship. So first weight is 8,000 ton, that is the weight of the ship. Now the total weight of the ship is acting through the center line only. So there is no lever. So that will be 0 here. So movement generated because of the weight about the center line, that will be 0 obviously. Now we have to see we have pumped out the water from the starboard side. So the weight of the water which is pumped out, that already we have done the calculation for that. That is coming 46.125. Now we are pumping out, so it will be like you are removing the weight, so it will be a minus here. Now you have to find out the lever of the weight which is removed or which is pumped out. You have to take the lever from the center line. So from the starboard side we are removing the mass or the cargo we are pumping out. So width of the starboard side is a 7.5 meter. So half of that will be 3.75 meters. So that we are writing here. I am taking plus sign towards the starboard side for the lever. So the moment which is coming here because of the weight minus 46.125 into 3.75, you will get this sign as a minus here. So the total movement, the summation of the movement, it will be minus 172.96. It means that whatever the value of a G1, G2 is coming, that will be minus 172.96 divided by summation of the weight. So the final value which is coming, that is a minus. What is the meaning of this? Minus means it will be in opposite direction to the weight which is removed. So we have removed the cargo, we have pumped out the water from the starboard side. So the G2 will be moved towards the port side. So this is the horizontal shift of G1 to G2. Now once you got the horizontal shift, now you have pumped out the water. Now on the starboard side, whatever the debit tank is there, it will have some free surface effect. The free surface effect will be G2 to GV, or if you project G2 to GV on the center line, it will be G1 GV. So G2 to GV and G1 GV both are same only in the magnitude. Okay, so how to calculate the free surface effect? So for that purpose, you can write the formula G1 GV is equal to I by W2. W2 means the weight or the displacement of the ship after the removal of the water, after pumping out the water. That W2 we have already calculated, that is W1 minus W, which is coming 7953.87 tons. Then rho is the salt water density. Now in this case n is the number of a compartment here. Now the free surface effect you can see only in the right side only. On the left side there is no free surface effect. So if you think only about the right side part, so here you don't think about this part, because there is no free surface effect on the left side. You have a free surface effect only on the starboard side. So here this compartment is not divided in any other compartments. It is a single compartment. So here n is equal to 1 only. N is equal to 1 only. Okay. Now how to calculate the I? I is the moment of inertia where the free surface effect is there. In that region only you have to calculate the I. So you have to take this is the length of the double bottom, and the width of this double bottom on the starboard side is 7.5 meter. So that LB cube by 12, if you do like that, you will get the value of I. All the values you can substitute here, you will get the value of a G1 GV, that is a 0.054 meter. So like this you will get the value of a G1 GV. Now you can see here the total weight. Now the center of gravity of the whole ship is shifted towards the port side. It means that the ship is going to incline towards the port side. So how much is the inclination towards the port side? That is called as the angle of list. How to calculate that? So to calculate the angle of list, we are going to use this formula. Tan theta is equal to G1 G2 divided by GVM. You see this triangle here. So the opposite side is this one, and this side both are same only, that is a G1 G2. So that G1 G2 divided by the adjacent side, that is a GVM. So how to calculate the GVM? GVM is equal to Km, which is a constant, minus Kg1 plus G1 GV. Km is given to us. Kg1 we have calculated, G1 GV we have calculated. Substitute all the values, you will get the value of a GVM. G1 G2 we have calculated in the last slide. You take these both the values, substitute in this equation, you will get the value of a theta is 3 degree and 04 minute to port. So this is a very important. If you are removing the cargo, if you are pumping out the water from the starboard side, the ship is going to list towards the port side. That is the very important thing that you need to understand. I hope all of you understood this numerical. We will have a discussion how to decide the value of n in the free surface effect formula. If you have seen that in earlier problems we have decided the value of n, then we will have a little bit more discussion on this. So I thought we will take different condition, and let me explain all the conditions on the same page, so it will be easy to understand how to decide the value of n. So there are 4 conditions I have taken here. So first condition, consider this is the DB tank. Let's consider this is the rectangle tank only, and now this DB tank is filled up to certain depth. So there is some free surface effect is coming here. This is the empty space. So there is a partial filled tank is there. Now this you can see in between that there is no partition over here. There is no vertical partition here. So In this case you can take the number of compartment is 1. Now coming to the second case, the same debit tank, but I am putting one full center girder. Full center girder means what? So from the bottom to the tank top, there is a one center girder is there. Again, it is a watertight center girder running along the length which is perpendicular to the screen. And both the tanks are partially filled. So in this case, you can take there are two compartments here. N is equal to 2. Now coming to the third condition where we have a half center girder, means the center girder is starting from the bottom of the ship to the up to the some height, and now there is a water here, there is some free surface effect, but the level of the water is above the top of the half girder. You can see it is passing here and center girder end is here, half center girder is end here. So in this case it is not working as a compartment 2, it is working as a compartment 1 only. You will have a N is equal to 1 only. But if you coming to the fourth case where again you have a half center girder, but the water level is up to the half of this half center girder. Now in this case you will have it is working as a N is equal to 2. There will be a working as a 2 compartments. So you can take N is equal to 2 here. I hope all of you understood how to decide the value of N when you are going to use the formula free surface effect. Thank you very much.